welcome to this TensorFlow session about reinforcement learning. So this is Johan, I'm Martin, and today we would like to build a neural network with you. Do you know about neural networks? If I say, a serious question, if I say softmax or cross entropy, raise your hand if you know what that is. Like half the audience. Okay, very quick primer. This is a neural network, okay? Layers of neurons. Those neurons, they always do the same thing. They do a weighted sum of all of their inputs. And then you can layer them in layers. The neurons in the first layer, they do a weighted sum of, let's say, pixels, if we are analyzing images. The neurons in the second layer will be doing weighted sums of outputs from the first layer. And if you are building a classifier, let's say here probably you want to classify those little square images into airplanes and non-airplanes, you will end up on a last layer which has as many neurons as you have classes. And if those weights are configured correctly, we'll get to that, then one of those neurons will have a strong output on certain images and tell you this is an airplane, or the other one will have a strong output and it will tell you, no, this is not an airplane. Okay? There is one more thing in this. There are activation functions. So a little bit more details about what a neuron does. For those who like it, you have the full, right here. You have the full transfer function here. So you see it's a weighted sum plus something called a bias. That's just an additional degree of freedom. And then you feed this through an activation function. And in neural networks, that is always a non-linear function. And to simplify for us here, only two activation functions that count. So for all the intermediate layers, the white layers, ReLU. That's the simplest function you can imagine. You have it on the graphic, okay, just this. It's non-linear. We love it. Everyone uses that. Let's not go any further. On the last layer, though, if you are building a classifier, typically what you use is the softmax activation function, and that is an exponential followed by a normalization. So here I have a different classifier that classifies in 10 classes, and you have your weighted sums coming out of your 10 final neurons. And what you do in softmax is that you elevate all of them to the exponential, and then you compute the norm of that vector of 10 elements, and you divide everything by its norm. The effect of that, since exponential is a very steeply increasing function, is that it will pull the winner apart. I made a little animation to show you, like this. This is after softmax, this is before softmax. So you see much clearer which of those neurons is indicating the winning class. Okay? That's why it's called softmax. It pulls the winner apart like a max, but it doesn't completely destroy the rest of the information. That's why it's a soft version of max. Okay, so just those two activation functions. With that, we can build the stuff we want to build. So now, coming out of our neural network, we have our, let's say here, 10 final neurons producing values which have been normalized between 0 and 1. We can say those values are probabilities, okay? The probability of this image being in this class. How are we going to determine the weights in those weighted sums? Initially, it's all just, random. So initially, our network doesn't do anything actually so useful. We do this through supervised learning. So you provide images which you have labeled beforehand. You know what they are. And on those images, your network is going to output this set of probabilities. But you know what the correct answer is, because you are doing supervised learning. So you will encode your correct answer in a format that looks like what the network is producing. It's the simplest encoding you can think of. It's called one-hot encoding. And basically, it's a bunch of zeros with just one 1 in the middle at the index of the class you want. So here, to represent the 6, I have a vector of zeros with a 1 in the 6th position. And now, those vectors look very similar. I can compute the distance between them. And the people who studied this in a classifier, they tell us don't use any distance, use the cross-entropy distance. Why? I don't know. They are smarter than me. I just follow. And the cross-entropy distance is computed like this. So you multiply element by element, the elements of the vector, the known answer from the top, by the logarithm of the probabilities you got from your neural network. And you then sum that up across the vector. This is the distance between what the network has predicted and the correct answer. That's what you want if you want to train a neural network. You get this, it's called an error function or a loss function. From there on, TensorFlow can take over and do the training for you. You just need an error function. So in a nutshell, those are the ingredients in our pot that I want you to be aware of. You have neurons. The neurons do weighted sums. You have only two activation functions that you can use, either the ReLU activation function on intermediate layers, or if you build a classifier on the last layer, softmax. And the error function that we are going to use is the cross-entropy error function that I had on the previous slide. Okay? All good on this? Bit of code. This is how you would write it in TensorFlow. So there is a high-level API in TensorFlow called layers, where you can instantiate an entire layer at once. You see, I instantiate the first layer. Here has 200 neurons and is activated by the ReLU activation function. It's this layer here. And this also instantiates the weights and biases for this layer in the background. You don't see that, it's in the background. I have a second layer here, which is, this one is just 20 neurons, again, ReLU activation function. And this I need to do this little final layer. So it's a dense layer again with 2 neurons. And even if you don't see it on the screen, it is activated by softmax, but you don't see it because I use its output in the cross-entropy function, which has softmax built in. So it is a softmax layer. It's just that you don't see written softmax in the code. Finally, this here is my error function, which is the distance between the correct answer here, one-hot encoded, and the output from my neural network. Once I have that, I can give it to TensorFlow, pick an optimizer, ask it to optimize this loss, and the magic will happen. So what is this magic? TensorFlow will take this error function, differentiate it relatively to all the weights and all the biases, all the trainable variables in the system, and that gives it something that is mathematically called a gradient. And by following this gradient, it can figure out how to adjust the weights and biases in the neural network in a way that makes this error smaller, that makes the difference between what the network predicts and what we know to be true smaller. That's supervised learning. So that was the primer. Now, what do we want to build? Today, we would like with you to build a neural network that plays the game of Pong. But just from the pixels of the game. It's notoriously difficult to explain to a computer the rules of a game and the strategies and all that. So we want to do away of all that and just give it the pixels and find some learning algorithm that will, where it will learn to play this game. And of course, that is not the goal in itself, because figuring out how to program a paddle to win Pong is super easy. You just always stay in front of the ball, you know, and you win all the time. And actually, we will train again such a computer-controlled agent. The goal here is to explore learning algorithms, because this has applications, hopefully, way beyond Pong. So this looks like a classifier. We just learned how to build a classifier. You know, we have the pixels, we will build a neural network, and it has 3 possible outcomes. This is a position in which you want to go up, stay still, or you want to go down. Okay, let's try to do this by the book in a classifier. So we have a single intermediate layer of neurons activated with ReLU, of course, and then a last layer where there's 3 neurons activated by softmax. we use the cross entropy loss. So you have the function here. It's the distance between the probabilities that this policy network, it's called a policy network, predicts, probability of going up, still, or going down, and the correct move. But what is the correct move? I don't know. Do you know, Johan?
No, Martin. You're exactly right here. Unlike in the supervised learning problem, we actually don't know what's the correct move to play here. However, the environment requires that we keep making moves of going up or staying still or moving down to progress again. And so what we're going to do is we're going to sample the move, which means picking one of the 3 possible moves of moving the pedal up, staying still, or going down randomly. But not completely randomly, though. We're going to pick the move based on the output of the network. So for example, if the network says the output probability of going up is 0.8, then we should make it so that there's 80% of chance we choose to move up as our next move.
All right, so now we know how to play the game. The policy network gives us probabilities. We roll a loaded dice and pick from that, and we know what next move to play. But initially, this network is initialized with random weights. So it will be playing random moves. How does that inform us about the correct move to play? I need to put the correct move in my formula.
That's right. So in this case, we really want the correct move to mean moves that will lead to winning.
Yeah.
We don't know that until somebody has scored a point. And so that's what we're going to do. Only when someone, either our pedal or the opponent pedal, has scored the point, do we know we have played well or not. So whenever somebody scores, we're going to give ourselves a reward. If our pedal scores the point, we'll give ourselves a +1 reward point. And if the opponent pedal scores, then we give ourselves a -1 reward point. And then we're going to structure our loss function slightly differently than before. Over here,
once again,
over here you see a loss function very much like the cross entropy function we saw before. Now in the middle here is the main difference, where instead of the correct label in the supervised learning problem, we're just going to put the sampled move in there.
So the move we played.
The move that we happen to play. And well, some of the moves might not be really moves that will help us. And so that's why every loss value is multiplied by the reward out front. This way, moves that eventually lead to a winning point will get encouraged, and moves that lead to a losing point will be discouraged over time.
Okay, so you do this for every move. I can see how with this little modification, it could lead to some learning, but putting back my mathematician's hat on, I see a big problem here. You have this sampled move. That is a picking operation, a sampling operation. You pick 1 out of 3. That is not differentiable. And to apply, the minimization and gradient descent and all that, the loss function must be differentiable.
You're right, Martin. Asking a hard question here. The sample move here, it actually does depend on the model's weights and biases, but the sampling operation is not differentiable. And so we're not going to differentiate that. Instead, we're going to look at the sampled moves as if they are constants. And then we play many games across many moves to get a lot of data, treating all of these sampled moves as if they are constant labels. And only differentiating the probabilities that are output by the model in blue here on the screen. And those probabilities directly depend on the model's weights and biases, and we can differentiate those with respect to the weights and biases. This way, we still get a valid gradient, and we can apply gradient descent techniques.
Oh, okay. So you kind of cheated the part that is problematic, just regard it as constant. You're going to play many games with the same neural network, accumulate those played moves, accumulate those rewards. Whenever you know that you scored a point, you accumulate those rewards. And then you plug that in, and you only differentiate relatively to the predicted probabilities. And yes, you're right. That still gives you a gradient that depends on weights and biases, so we should be able to do that. Okay, I get it. This is clever. So this will actually train, probably very slowly. Here we want to show you the minimum amount of stuff you need to do to get it to train. But in the minimal amount, there are still two little improvements that you always want to do. The first one is to discount the rewards. So probably if you lost a point, you did something wrong in the 3, 5, 7, 10 moves right before you lost that point. And probably before that, you bounced the ball correctly a couple of times, and that was correct. You don't want to discourage that. So it's customary to discount the rewards through time, backwards through time, with some exponential discount factor, so that the moves you played closest to the scoring point are the ones that count the most. So you see here we discounted them with a factor of 1/2, for instance. And then there is this normalization step. So what is that?
Yeah, that's very interesting. So in experiments that we noticed, putting in the normalization step really helped training to make learning faster. There are probably multiple ways to think about this. The way I like to think about this is in the context of playing a game. You see, at the beginning of the time, the model only had randomized weights and biases, so it's going to make random moves. So most of the time, it's not going to make the right move. Only once in a while, it's going to score a point, but that's really by chance, by accident. And most of the time, it's going to lose points. And we really want to find a way to naturally put more weights to the very rare winning moves there, so that I can learn what are the correct moves. And performing this normalizing the reward step here naturally gives a very nice boost to the rare winning moves, so it does not get lost in a ton of losing moves.
Okay, so let's go. Let's train this. We need to play the game and accumulate enough data to compute everything that we need for this function here, okay? So those are the sampled moves, we need the rewards, and we also need those probabilities which the network can compute from us from the pixels, so we are going to collect the pixels during gameplay. That's how our collected data set looks like. Okay, you have one column with the move you actually played, one column where you would like to see the probabilities predicted at that point, but you will actually going to store just the game board and run the network to get the probabilities, and the last column with the rewards. You see there is a +1 or -1 reward on every move that scored a point, and on all the other moves, you discount that reward backwards in time with some exponential discount. So that's what we want to and once you have this, maybe you notice in the formula, you just multiply those 3 columns together and sum all of that. That's our loss. That's how the loss is computed. Let's build it. You implemented this demo, so can you walk us through the code?
Let's do that. So up here, you see a few TensorFlow placeholders. You should really think of them as function arguments that are required to compute output values for a model. And so with 3 placeholders for the input, 1 for the observation. And remember, this really means the difference between 2 consecutive frames during a gameplay. And the action...
Oh yes, because we didn't say that actually. Just in the game of Pong, you don't really train from the pixels because you don't see the direction of the ball from just the pixels.
Exactly.
But you train from the delta between 2 frames because there you see the direction of the ball. That's the only wrinkle we are doing here which is specific to Pong. All the rest is reinforcement learning, vanilla reinforcement learning that applies to many other problems.
That's right.
Yeah.
And for the actions placeholder, it's just going to hold all the sampled the moves that the model happen to decide to play. And the rewards placeholder will collect all the discounted rewards. Now with those as inputs, we're ready to build a model. The network is really simple. It's like the one Martin showed before. It has a single dense layer, a single dense hidden layer with the activation of the ReLU function, 200 neurons, followed by a softmax layer. You don't really see calling a softmax function here, and that's really because the next step, the sampling operation, already takes in logits, which is the values you get before you call softmax function, and it can perform multinomial sampling, which just means it will output a random number of 0, 1, or 2 for the 3 classes that we need output based on the probabilities specified by the logits.
And this one has the softmax built in, so...
Already built in internally.
So this is a softmax layer, okay?
That's right.
You don't see it on the code, but it is. Okay, and just a parenthesis for those not familiar with TensorFlow. TensorFlow builds a graph of operations in memory. So that's why out of multinomial we get an operation, and then we will have an additional step to run it and actually get those predictions out. And placeholders are the data you need to put in when you actually run a node to be able to get a numerical result out. Okay, so we have everything we need to play the game. Still nothing to train. So let's do the training part. For training, we need a loss function. So our beloved cross-entropy loss function, computing the distance between our actions, so the moves we actually played, and logits, which are from the previous screen. That's what the network predicts from the pixels. And then we modify it using the reinforcement learning paradigm. We modify it by multiplying this per move loss by the rewards, by the per move rewards. And now, with those rewards, moves leading to a scoring point will be encouraged, moves leading to a losing point will be discouraged. So now we have our error function. TensorFlow can take over. We pick one of the optimizers in the library and simply ask this optimizer to minimize our loss function, which gives us a training operation. And when we will, on the next slide, run this training operation, feeding in all the data we collected during gameplay, that is where the gradient will be computed, and that's the operation, when run, that will modify the weights and biases in our policy network. So let's play this game. This is what you need to do to play one game in 21 points. So the technical wrinkle is that in TensorFlow, if you want to actually execute one of those operations, you need a session. So we define a session. And then, in a loop, we play a game. So first, we get the pixels from the game state, compute the delta between two frames. OK, that's technical. And then we run session.run this sample operation. Remember, sample operation is what we got from our picking multinomial function. So that's what decides the next move to play. Then we use a Pong simulator here from OpenAI Gym. We can give it this move to play, and it will play the move and give us a new game state, give us a reward if we scored a point, and give us information on whether this game in 21 points is finished. Okay? That's all we need. Now we simply log all that stuff. We log the pixels, we log the move we played, we log the reward if we got one. So we know how to play one game, and we will play many of those games to collect a large backlog of moves, right?
That's right. Playing games in reinforcement learning or in our experiment really is a way of collecting data. Now that we have collected a lot of data, playing one game or maybe 10 games, why not? We can start processing rewards as we plan to. We will discount the rewards so that the moves that did not get any reward during gameplay now gets a discounted reward based on whether or not they eventually led to winning or losing points and how far they are from the moves that actually won or lost a point. And then we normalize those rewards as we explained before. Now we're ready. We have all the data in place. We have observations. That's the differences between game frames. The actions that we haven't played, and the rewards so that we know if those actions were good or bad. And then we're ready to call the training up. And training up is what we saw a couple slides before, where we had optimized already initialized, and this is going to do the heavy lifting and compute the gradients for us and modify the weights just slightly. Suppose we play 10 games, we modify the weights slightly, and then we'll go back and play more games to get even more data and repeat the process. And the expectation or the hope is that the model will learn to play a little bit better every time.
I'm a bit skeptical. Do you really think this is going to work?
Well, sometimes we see the model actually learn to play a little bit worse, so we'll see.
Okay, live demo?
Live demo.
Let's go. Let's run this game. So this is a live demo. I'm not completely sure that we are going to win, but we shall see. So brown on this side is the computer-controlled paddle. Very simple algorithm. It just stays in front of the ball at all times. So there is only one way to win. Its vertical velocity is limited, so you have to hit the ball on the very side of the paddle to send it at a very steep angle, and then you can overcome the vertical velocity of the opponent. That's the only way to score. On the right, in green, we have our neural network controlled agent. And it's slightly behind now. So we'll see if it wins. And if you want, I want this side of the room to cheer for Brown, and this side of the room to cheer for AI. Okay? So it's very even right now. Yeah, go. AI is winning. I'm happy because this is a live demo. There is no guarantee that AI will actually win. One thing that is interesting here, actually, is that this is learning from just the pixels. So initially, the AI had no idea of even what game it was playing, what the rules were. It had even no idea which pedal it was playing, okay? And we didn't have to explain that. We just give the pixels, and on scoring points, we give a positive or a negative reward, then that's it. From that, it learns. And you see those emerging strategies, like what I said, hitting the ball on the side and sending it at a very steep angle is the only way of winning. And it picked that up. We never explained it. It's just an emerging strategy. This is looking good.
Pretty close. Yeah.
It's looking good. It's a bit close, but it's looking good. You think we'll win? Okay, next point, I want a loud cheer when AI wins. Because I hope this is going to work. Hey, 20? Okay, one more. Yeah, we won.
We've done it.
Good job, Johan. This is fantastic. All right. So, what was going on during gameplay? Actually, remember how this network was built? Right here. So, neurons in this very first layer, they have a connection to every pixel of the board. They do a weighted sum of all the pixels in the board, all right? So they have a weight for every pixel, and it's fairly easy to represent those weights on the board and see what those neurons are seeing on the board. So let's try to do that right here. Oops. We picked 8 of those 200 neurons, and here we visualize, superimposed on the board, the weights that have been trained. And the untrained eye doesn't see much in here. So maybe you can enlighten us, Johan.
This is really interesting, Martin. We're looking at what the model sees, or rather what the model cares about when it sees the game pixels that we gave it. You see that one of the neurons apparently had learned pretty much nothing. It's still looking like a white noise at the beginning of initialization.
Yeah, bad pupil here. Didn't listen.
So it probably did not contribute much to the gameplay. But for all the other neurons, you see some interesting patterns there. We see a few things that the model seems to put a lot of weights on. It cares a lot about where the opponent paddle is and where it's moving. And also cares about the ball's trajectory across the game board. And quite interesting, it also cares a whole lot about where its own paddle is on the right. Because like Martin pointed out before, at the beginning of learning, the model didn't even know which paddle it's playing. And so it has to learn to remember that's an important piece of information to be able to play game well. And when you think about this is really consistent with how we human beings will believe consists of important informations to be able to play the game well.
So we wanted to show this to you, not to show our prowess at Pong, although it worked, but mostly to explore training algorithms. And you see, mostly in neural networks, you do supervised training. And in nature, well, sometimes when we teach people, it looks like supervised training. Probably in class, the teacher says, this is the Eiffel Tower, and the pupils say, oh, okay, that's the Eiffel Tower, and so on. But if you think about a kitten jumping on a fur ball and missing it, and jumping again until it catches it, and there is no teacher there. It has to figure out a sequence of moves, and it gets a reward from catching the ball or not catching it. So it looks like in nature there are multiple ways of training our own neural networks, and one of them is probably quite close to this reinforcement learning way of teaching. Johan, you built this model. Is there some other thoughts it inspired you?
Yeah, I have a sort of technical insight maybe for you as a takeaway message. In running experiments, we see that there are some steps which are not differentiable. particularly in this case, sampling a move or the probability output from a network and playing the game and getting a reward back. Yes, those factors really do depend on the model itself, but in a non-differentiable way. And so even with the powerful tools like TensorFlow, you wouldn't be able to very naively build a loss function and then run gradient descent training. But there are ways to get around it, and that's exactly the techniques we're showing today.
So what you're saying is that reinforcement learning can solve many more problems than just Pong, and it's a way of getting around some non-differential step that you find in your problem.
You should be able
That's
to do that.
great. That's great. So where is this going? We want to show you a couple of things from the lab, because this has had mostly lab applications. And then one last thing. What is this?
This is very interesting, everyone. What we're witnessing here is a human expert of pancake flipping trying to teach a robotic arm doing the same thing. And there's a model in the back supporting a robotic arm whose output controls the joints movement or the motors in it, what angle, what speed to move toward. And the goal of this is to flip that pancake. And the pancake is not just any regular pancake, but rather it's instrumented with sensors so that it knows if it's been flipped, if it landed on the floor or on the table or back in the frying pan.
Doesn't seem to be working.
It's trying, it's trying. In another experiment,
And so what is the reward here?
the reward probably is that if you flip the pancake correctly, then you get a positive reward and otherwise negative reward.
Okay.
And speaking of reward function, in another experiment, I was going to say, the experimenters set the reward to be a small amount of positive reward for any moment the pancake is not on the floor. And that machine learned, but what it learned was to fling the pancake as high as possible to maximize pancake airborne time. Never thought I would say something like that. That way it can maximize the reward just because it takes a long time for it to land on the floor.
So that's kind of funny, but actually it's a nice illustration of the fact that you can change the learned behavior by changing your loss function.
Exactly. The model learns.
That's how you teach it stuff.
Now it has learned.
Oh,
flip
nice.
pancake.
Yeah, cool. We know how to play Pong and flip pancakes. That's significant progress. DeepMind also published this video. So they used reinforcement learning, and they built those skeletal models. Here, the neural network is predicting the power to send to the simulated muscles and joints of these models. And the reward is basically a positive reward whenever you manage to move forward, and a negative reward when you either move backward or when you fall through a hole or when you just crumple to the ground. The rest is just reinforcement learning as we have shown you today. So all of these behaviors are emerging behaviors. Nobody taught those models. And look, you have some wonderful emerging behaviors. It's coming in a couple of seconds. Look at this jump. After this, those are nice jumps, but there is a much nicer one. In a second, you will see a jump, really athletic jump, with the model swinging arms to get momentum, then lifting one leg, cushioning right here. Look at this. This is a fantastic athletic jump. It looks like from the Olympics, and it's a completely emerging behavior.
But Martin,
what is it with the arm
if
movements?
this is an optimized way of walking and running, why do I not see people doing this? I mean, I could, but
Well, you know, there are multiple ways of running. Probably the loss function didn't have any factor discouraging, useless movements. So again, by modifying the loss function, you get different behaviors. And actually, one last one, not this one. This one is kind of funny. Yeah, still playing around. But I like look here. It figured out how to run sideways. This is fantastic. Yes, there are two ways of running, and it did figure out how to move sideways. This one you've probably seen. This is move 74 in game 4 of AlphaGo versus Lee Sedol. And that's the one move that Lee Sedol played that was called the God move, and he's world famous for just that. He played one correct move and managed to win one game against AlphaGo. He lost 4-1, which is fantastic. And AlphaGo also uses reinforcement learning, not exactly in the same way. Here, it wasn't entirely built out of reinforcement learning, okay? Because for turn-based games, the algorithm for winning is actually quite easy. You just play all the moves to the end and then pick the ones that lead to positive outcomes. The only problem is that you can't compute that. There are too many of them. So you use what is called a value function. You unroll only a couple of moves, and then you use something that looks at the board and tells you this is good for white and good for black, or good for black. And that's what they built using reinforcement learning. And I find it interesting because it kind of emulates the way we humans solve this problem. This is a very visual game. We have a very powerful visual cortex. When we look at the board, Go is a game of influence, and we see that in this region, black has a strong influence. In this region, white has a strong presence. So we can kind of process that. And what they built is a value function that does kind of the same thing and allows them to unroll the move to a much shallower depth. Because after just a couple of moves, their value function, built using reinforcement learning, tells them this is great for white or good for black. So these are results from the lab. Let's try to do something real. So some application. What if we build a neural network? It's a recurrent neural network. Okay, that's a different architecture of neural network, but for what you have to know, it still has weights and biases in the middle, okay? And this neural network, recurrent neural networks, are good for producing sequences. So let's say we build one that produces sequences of characters. And we structure it so that those characters actually represent a neural network. Yeah, a neural network is a sequence of layers. So you can figure out a syntax for saying, this is my first layer, this is how big it is, and blah, blah, blah. So why not produce a sequence of characters that represents a neural network? What if then we train this neural network on some problem we care about? Let's say spotting airplanes in pictures. So this will train to a given accuracy. What if now we take this accuracy and make it a reward in a reinforcement learning algorithm? So this accuracy becomes a reward, and we apply reinforcement learning, which allows us to modify the weights and biases in our original neural network to produce a better neural network architecture. It's not just tuning the parameters, we are changing the shape of the network that works better for our problem, the problem we care about. We get a neural network that is generating a neural network for our specific problem. It's called neural architecture search, and we actually published a paper on this. And I find this a very nice application of a technology designed initially to beat Pong.
So Martin, you're saying we have neural networks that learn to build other neural networks.
Yeah.
That's deep, man.
Yeah. So Johan, to finish, you built this demo. So can you tell us a word about the tools that you used?
Yeah, definitely. So we use TensorFlow for the model itself, and TensorBoard for tracking the metrics of during the process of training. I really didn't want to run the training on my laptop, but I probably could, so I used a cloud machine learning engine for the training. The model that was playing the game that we saw before the live demo took maybe about 1 day of training to accomplish that.
And so with ML Engine, you have this job-based view, and you can launch 20 jobs with different parameters.
In fact, that's what I did.
And just let them run. And it's just practicality, right? It will tear down the whole cluster when every job is done and so on.
That's right. Worry-free.
Yeah, I use ML Engine a lot as well for that. There are many other tools in cloud for doing machine learning, but one we just launched is AutoML Vision. That's one when you do not program, you just put in your labeled data, and it figures out the model for you, and now you know how it works. And also, this uses lots of CPU, GPU cycles, so cloud TPUs are useful when you're doing neural architecture search, and they are available to you as well now. So, thank you. That's all we wanted to show you today. Please give us feedback. We just released this code to GitHub, so you have the GitHub URL. If you want to train a Pong agent yourself, go and do it. You can take a picture there. And if you want to, the URL is still on the screen. If you want to learn machine learning, I'm not going to say it's easy, but I'm not going to say it's impossible either. We have this series a relatively short series of videos and code samples and code labs called TensorFlow without a PhD that is designed to give you the keys to the machine learning kingdom. So you go through those videos. This talk is one of them, and it gives you all the vocabulary and all the concepts, and we are trying to explain the concepts in a language that developers understand because we are developers. Thank you very much.